Hello and welcome. In this video, we are going to investigate some vector spaces that are closely linked to a matrix. We have already seen that the space of matrices itself is a vector space, but a matrix is often used as a convenient way to define other vector spaces, and those will play an important role in different contexts. For example, when talking about solution spaces of systems of linear equations. We therefore define those vector spaces formally and give them a proper name right now. So this chapter is called Vector Spaces Associated with a Matrix. And one major idea here is to just use the rows or the columns of a matrix to generate a vector space. So for example, if you look at the columns of a matrix, then you can have a look at the vector space that is spanned by these columns, and similarly for the rows. And these vector spaces may be important in certain contexts, but also that it can serve as a very convenient way of writing down certain vector spaces. So let's define that formally. What we need, of course, is a matrix. So let A be a matrix with entries Aij. And let's say we have an M by N matrix as usual. And now we define the rows and the columns in a suitable way. We've done this before already, but just as a quick recap. So let Cj, call that the jth row. And again, that is the vector consisting of the entries A1j to Amj. That's a vector in R to the M. Be the jth. Oh, sorry, it's the jth column, of course, not the jth row. That was a mistake. The jth column of A. And similarly, we'll have the jth row of A, or the ith row, rather, to differentiate that properly. Now, that's usually the row AI1 to AIN. And in this context, we'd like to have vector spaces in the form of column vectors only, so we will transpose that vector here, just to have all columns for all involved vector spaces. It doesn't really make much of a difference, at least not at this point. So let that be the ith row of A. And then we introduce the following vector spaces. The first one is going to be the column space. Is the vector space that is written as call space of A and is defined as the span of the column vectors. Very simple. So just the span of C1 to Cn. Remember, we have n columns. That's the column space of A. Part 2. In a similar way, we can also define a row space, of course. So the row space of A is the vector space. I will denote this as row space. And that's the span of the row vectors, unsurprisingly. So R1 to Rm, we have m rows. And finally, one more space that is often used in the connection with matrices, that is the so-called kernel, or sometimes called null space. The kernel or null space of A is the solution space of the system of linear equations denoted by the coefficient matrix A and the right-hand side 0. And the kernel is denoted by ker of A, or sometimes kern of A. Quick example. Let's take the matrix 2, 1, 1, 2, 1, 0, like this. Then the column space of A is the span of its columns. So column space of A is equal to the span of 2, 1, 1, 2, and 1, 0. So we just take the 3 columns as single vectors and take their span. And obviously in this case, this is R2 because we have at least 2 linear independent vectors in that set, so that would span the whole R2. The row space, that's a different beast here. The row space of A is the span of the rows. And those rows are 2, 1, 1 and 1, 2, 0. So that's 2 vectors in R3, and obviously that cannot span R3 because that would be 3-dimensional, but it is a subspace of R3. And finally, let's have a look at the kernel. So for the kernel, we'll need to solve the associated system of linear equations here. We'll do this by using Gaussian elimination. So we just subtract 2 times, sorry, not 2 times. We just subtract half of the first row from the second one. And that will yield, let's see, a 0 here. 2 minus 1 over 2, that will be 3 over 2. And minus 1 over 2 here. That's a 0. So what we get is, well, x3 is a free variable. Here's a pivot and here's a pivot. So we have pivots associated to x1 and x2. The second row gives us the equation 3 over 2x2 equals 1 over 2x3. So that means x2 is equal to x3 over 3. And the first row gives us the equation 2x1 equals minus x2 minus x3. x2 is x3 over 3, so that is minus x3 over 3 minus x3. So minus 4 over 3 x3. And that means x1 is 2/3 x3. So our solution space, and that is the kernel that we are looking for, the kernel of A, is then the following space. We have our variable x3. That's the free one. We have x2, that is x3 over 3. And we have x1, that is not 2 over 3, but minus 2 over 3, I'm sorry. That is minus 2 over 3 x3, like this. x3 in the reals. So in other words, this is the span of minus 2 over 3, 1 over 3, and 1. So as you can see, the kernel is again a subspace of R3. Okay, and finally, we'll transfer one important fact that we know about systems of linear equations to this new world of matrices. And this theorem that we basically know already in different contexts, that is called the rank nullity theorem. And it will be frequently helpful to know that. Basically what it says is, if we have a matrix and regard this as a coefficient matrix of a system of linear equations, then the number of free variables is the same as n, the columns, minus the number of pivots. You know that already. And this number of pivots is called the rank of the matrix or of the system of linear equations. You know that already as well. So we can now formulate that in a very compact way. Now it looks like this. So for a matrix A in R to the m by n, we have 1. The rank of A, the rank is the number of pivot elements. You remember that? That is the same as the dimension of the column space of A, because that number of pivots basically gives you the number of linear independent columns in A. And of course, that is also the same as the dimension of the row space. Because again, if you look at the rows, the number of pivots gives you the number of linearly independent rows of A. Yeah, so that's exactly the same thing as the number of pivots if we regard A as a coefficient matrix. So row space and column space have the same dimension. And second, the number n, the number of columns of that matrix, is the rank of A plus the number of free variables. And the number of free variables is the dimension of the kernel of A. Because if you solve the linear equation system associated to A with right-hand side 0, then the number of free variables in that system tells us the dimension of the associated solution space, and that is the kernel. So that is rank A plus dimension of the kernel of A. And remember, that is the same thing as the number of free variables, and the rank is the same as the number of pivots. So you know that theorem already, and now we formalized it for matrices. Have a look at the examples here. If you compare first the column space and the row space, You'll notice the row space is two-dimensional. You can see that here in the last row, for example. These two vectors are obviously linearly independent, so the row space here is two-dimensional. And the column space, well, the column space is R2. So obviously the dimension of that is 2 as well. Yeah, so you will notice that those two agree. And if we have a look at the kernel, then we can see that the dimension of the kernel of A is 1. And that is exactly equal to n, which is 3, minus the rank of A, which is 2. So if you solve a system of linear equations, or if you compute the rank of a matrix or the kernel of a matrix, you should always bear in mind this rank nullity theorem, just as a ways of quickly checking whether your results actually make sense. The dimension of the kernel of A and the rank of A always need to sum up to n. Otherwise, there will be a mistake somewhere. And of course, that also helps you to get access to one of those two dimensions without actually computing it. Yeah, if you have one already, you don't have to compute the other. Okay, that concludes our introduction of important vector spaces associated with a matrix. We'll frequently make use of those spaces later on. That concludes today's video. I'll see you in one of the upcoming videos.